Thank you, Valerie. Hello, everybody. So, first of all, I want to thank the organizer for inviting me. It's a big pleasure to be here today. So I am lecturer at the Jean-Laurent d'Alembert Institute in Sorbonne University. Yes, I am a lecturer at Sorbonne University in the Institute Jean-Laurent d'Alembert, that is a laboratory of mechanics. And my main researches focus on the propagation of acoustic or elastic wave in heterogeneous media, but I work also on other topics such as the propagation of elastic guided wave or the ultrasonic characterization of viscoelastic materials. But today I'm going to talk to you about a big part of my recent researches on the propagation of coherent elastic wave in multiple scattering media, and especially I want to focus this work on the influence of resonances and positional correlations between scatterers. I want also to give you the name of my collaborators, that are Jean-Marc Renoir from the modelings, and Régis Valier-Brasier and Régis Marciano. They are also working on the Institute d'Alembert Institute. So, the wave propagation in heterogeneous media is an old and fundamental topic. Ultrasound are used for many years to characterize heterogeneous media such as colloids or composite materials, and this topic has received renewed interest with the advent of metamaterials. These materials are heterogeneous materials that are created in order to control and filter the wave. Among the different strategies, we find the phononic crystals that are periodic arrangements of scatterers in a matrix, and we find also on the other side, the locally resonant metamaterials that are random or periodic distribution of scatterers that exhibit strong subwavelength resonances. So, more recently, another strategy has appeared. It is based on the use of correlated distributions of scatterers in order to control the wave. So, the topic of the propagation, the wave propagation in heterogeneous media is an old problem, and there are lots of studies on this topic, obviously. For the experiments, there are lots of measurements that have been performed on heterogeneous liquids. So, different parameters have been measured, such as the phase velocity, group velocity, attenuation of the coherent wave, scattering and transport minute passes, and so on. If we look for the solid materials, there are few results on experimental measurement in solids. We know that in 80s, Kinara and co-workers measure the coherent longitudinal wave in a random distribution of spheres embedded in viscoelastic resin, but there is no data on shear wave propagating in solid heterogeneous media in the literature. So, the measurement of coherent elastic wave, both longitudinal wave and transverse wave in multiple scattering media, is always a very important issue for the multiple scattering community. Now, for the modelings, the propagation is more balanced between fluids and solids. Lots of numerous different approaches have been proposed in literature, such as for the most famous, the coherent potential approximation, multiple scattering series using scattering T matrix or Lune function, a diagrammatic representation, dynamical homogenization, and so on. For my topic of the propagation of coherent elastic wave, the question is, among all these models, which ones are suitable for solid matrices, and therefore for coupled longitudinal and transverse elastic wave, for the strong scattering effects due to resonance and especially for sub-wavelength resonances, and also for positional correlations between particles. So because there are few experimental results on this topic in the literature, we need a robust tool, numerical tool, to describe properly the propagation in resonant and or correlated solid media. So in this talk, I will talk to you about the coherent elastic wave, and I will present some modelings that we have done in the Institut Jean-Laurent d'Alembert, but we have also made experiments on solid media, and we compare both approaches as when it is possible. So let us start by the modeling of the propagation of elastic wave in multiple scattering media. It is a big part of my research that I perform with Jean-Marc Connoir in the Institut Jean-Laurent d'Alembert. We make with Jean-Marc, we develop a statistical model to describe the propagation of coherent elastic wave in multiple scattering media. And now I want to show you a collaboration that we have done with Francine Huppé at the University of Le Havre in France. We have adapted the model of Futurist and Waterman that is derived initially for electromagnetic wave. We have adapted this model to the case of elastic wave with coupling between longitudinal and shear wave. I will not give the details of this modeling, but just only the assumptions, because this assumption will be very important for the following of this talk. First of all, the model is based consists of the resolution of the multiple scattering equation, and we use the quasi-crystalline approximation, and we take also the alteration that introduces an exclusion distance p between particle pairs, and this exclusion distance is set to 2r, that is the diameter of each p. This parameter comes from the alteration, but it reflects the non-overlapping condition. So to solve the multiple scattering equation for elastic wave, we have to do, due to shear wave polarization, we have to use vector spherical harmonics expansion of the exciting field and of the coherent field that propagate in the multiple scattering net. So then, using the Lorentz-Varad's law, we obtain a linear set of equations, delta dot x equals 0 here, and x represents a vector that contains all the amplitudes of the coherent wave. So now, when we have this set of equations, we can extract the effective wave number by solving this characteristic equation here that comes from the vanishing of the determinant of the matrix here, delta. This exact effective wave number is obtained numerically, obviously. Nevertheless, we have made calculation in order to obtain an approximate expression for the effective wave number, both for longitudinal and shear coherent wave, and this is the expression that we obtain with a first order term in concentration and another second order term. In this second order term, you have to see here that we have coefficient that depend on scattering coefficient, but in the second order term we have a scattering coefficient that reflects the wave conversion between longitudinal to shear wave and shear to longitudinal wave. So I will use not in the following slide, but maybe in the last of my talk, this expression, but I will come back also on this method of resolution. So in parallel of the development of the statistical model of multiple scattering, we have also developed a numerical simulation code called MUSCA during the PhD thesis of Adrien Roufrich. Adrien Roufrich was, I think, at the second workshop months ago. So the modeling is behind the MUSCA code to solve numerically the multiple scattering equations. So if we consider, I present you only the 2D case with cylinders, but we are working also on the spherical case. And here we adapt this code to the case of elastic wave. So we take into account longitudinal and shear wave. So we assume, we consider different cylinders with different elasticity and different radii, and we have an incident wave that can be a plane wave, that can be also a point source. In this distribution, we have first to define the coordinate system associated to each particle. Here. And we have to define also the cylindrical harmonics, the cylindrical harmonic Cn that is associated to Bessel function Gn, and the cylindrical harmonic Tn associated to the angle function Hn. So these cylindrical harmonics are associated to each coordinate system. So now, if we consider an incident plane wave, we have to extend the potential associated with this wave to the cylindrical harmonics Cn. The incident plane wave can be longitudinal or a shear wave. So we have also to expand the scattered wave, the potential associated to a scattered wave on cylindrical harmonics. First of all, we have to say that the scattered field in the whole medium is the sum of the scattered field by each particles. And the scattered field by each particle is expanded on the cylindrical harmonics Tn without going wave. And we have here the coefficient Pn, Pm that are the amplitude of this expansion. This is the unknown of our problem. If we can determine this coefficient, we will be able to calculate the field, displacement field or stress field in the whole composite medium. So to obtain this coefficient, we calculate the incident field that is coming on the cylinder P. So we can say that the incident field that is coming on a unique cylinder is the sum of the incident plane wave that is propagated, that propagates in the homogeneous matrix, and it is the sum of the wave scattered by all the other particles. So using the cylindrical expansion, we obtain an expression here with the case for the expression for the incident wave, and here the expansion for all the other particles, for the scattered wave by all the other particles. The problem here is we have an incident field that is described in different coordinate systems. So we have to change this expression to express. We have to change the potential to express them in a unique coordinate system. To do this, we use the graph addition theorem that allows us to express the harmonics T in a cylindrical in a coordinate system of the Q particle into an expansion as a cylindrical harmonics associated to the coordinate system of the P particle. So using this graph addition theorem, we can change here this expression of the cylindrical harmonics, and we obtain the incident wave that is coming on the cylinder P, and it is expressed. It is an expansion of the on the cylindrical harmonics on the cylinder. It is well known in the theory of multiple scattering, and now we have applied this case to elastic wave. But we have not finished. Now we have obtained the expression of the incident wave expanded on the cylindrical harmonics of the cylinder P. We can use the scattering matrix here of the particle P, and we can link the amplitude of the scattered wave by the cylinder P as function of the incident wave, the expansion of the incident wave, the expansion which takes into account all the amplitude of the scattered wave by all the other particles, and the scattering matrix. We have an equation only for the particle P, but we can generalize this function, this equation, sorry, and we obtain the following set of equations. So it is a matrix equation that is solved by block matrices, sorry. We can see that we have the matrix PM1, M2 that appears here and here. This matrix is defined from the scattering matrix of each scatterer. So this matrix takes into account all the scattering, multiple scattering, all the scattering events. We have also the matrix QM here and here. This matrix expresses all the interactions between the particles. It is read from the graph addition symbol. We have also the coefficient Fm here that expresses the incident wave in the heterogeneous medium. And by inverting this matrix, we can obtain the coefficients Bl and Bt of the longitudinal scatter wave and of the transverse scatter wave. So now we have the amplitude of the scatter wave. We can read the, calculate the field in the whole composite material. So we do that just in a simple case. We want to calculate the displacement field, the potential field, sorry, in the case of the interaction of a plane longitudinal wave with a slab containing cylinders. We have a random distribution of scatterer or circular scatterers that are contained in a slab with parallel surfaces, and we have a longitudinal plane wave that comes from the left and interacts with the slab. We can calculate in few seconds we can calculate the potential CL associated to the longitudinal wave in the wall medium and the potential CT associated to the shear wave. We cannot extract something from this result. It's a very qualitative result, but we can perform a configurational average on these potentials. So we calculate the potentials CL and Phi for different distributions, and we take the mean value of this potential. So you have here the mean potential for the longitudinal wave, and here for the shear wave. You can see here that we can see the plane wave coming from the left. Here, the plane wave is the incident wave that resists to the average, and as it enters, this wave enters into the heterogeneous slab, it becomes a coherent plane wave, and we can see that there is attenuation of the coherent plane wave as it propagates inside the slab.
So what happens if the lateral boundaries in Y is a periodic condition?
No, there is no periodic distribution condition.
You've done that.
The slab is very long. I show you just a cut. Okay, but for good question, because for plane wave we have to take very large slab.
So outside that you have nothing. So you just have a finite long strip.
No, we have particles, but there are ends.
Yeah, there's ends.
Where does the energy go?
Sorry?
Where does energy go? Because if you don't have attenuation, so you don't have a shear wave, you have a spin wave, and where does energy go? Attenuation?
It is attenuated by multiple scattering. Yeah. So the energy is dissipated by scattering in the wall medium, and this is the mean. This is the mean potential. So with interference constructive and destructive, we cannot see the energy, but we have wave conversion. We can see here that we have wave conversion.
Dissipation energy cannot go anywhere. It can convert to one to another, but cannot be.
there is no dissipation, but a coherent wave can attenuate with by scattering.
You're not plotting the coherent field, you're plotting the total field. Well, you're doing a numerical simulation where you're not actually trying to pick out the coherent plot of the field, you're just plotting the scattered field in its entirety.
This is the total field.
Yeah.
This is the total field. This is the total field, but this is the mean total field.
Averaged it over.
And here we represent just non-emulsions with the emulsions right?
Yes, but not exactly, because I am in the project wave number to radius is larger to 1, so we have forward scattering. We are in a case that we have not most of the scattered wave goes forward. Okay, we have not. Well, we can see here that on the mean potential, we can see here that the incident wave is resists to the average, and there is no backscattering. There is no backscattering, but there is no also scattering perpendicularly to the direction of propagation. This scattering is very weak.
So how many configurations have you done in your averaging?
200.
200.
In fact, the number of distributions that we have used depend on the frequency. In low frequency regime, sometimes 10 or 20 distributions are sufficient, but in high frequency, we need more. No. Yeah, the number is fixed. What is the only thing that changes? This is the position of the particle. If we have the same concentration, the same number of particles with the same geometrical plot.
Use full correct.
Yes. I use all correction for this part in the following of my talk. I present results. We need, I compare often results with experiments, and all correction is complicated to implement with samples.
So one more question. The size of the scatterers that were represented is pretty small. They're the scatter sizes of the scatterers that are represented. It's about
They're the actual size of the scatterers that you used, or
diameter is
or
something like the wavelength.
In this case, I don't know, it's a millimetric scatter. What is the question? The wavelength, it's smaller than the wavelength, smaller than the particle.
oh, wavelength is smaller.
Yeah. I am in the high frequency region, not high frequency. The product wave number radius is superior to 1, maybe 1, 2. Okay. Yeah, sorry. Maybe for the presentation of this talk, I forget, I take not the good one. Yeah, in this case, you're right. I think the wavelength is temporal. The wavelength is, I don't know.
No, I finally asked about the shear component. So here we've got an incident longitudinal, and we've got something happening. There is a shear field. It's quite hard to deduce what the shear looks like from the potential of the shear field, and it's averaging out to something which is quite low in amplitude compared to the longitudinal field. What does that look like on average? What is the shear field like?
It's a complicated question. In fact, it is complicated to extract something from the potential of the shear wave. In fact, here we have a longitudinal incident wave, so we are studying a coherent wave because we have a ballistic propagation. In this case, there is no source, primary source. The shear wave is scattered by wave conversion.
normal population?
So we are, to my point of view, we are here in the diffusive regime because there is no source. Okay?
So in the statement there was no wave conversion, no wave.
Here, it is wave conversion. This is wave conversion here.
No, but if you start with coherent sound wave and you reflect from something, abnormal is coherent sound wave, you cannot have shear wave in the same field or synthetization, based on synthetization.
No.
Normal incidence, no back shear.
No. For you say about homogeneous media, I am. It is more complicated because when the longitudinal incident wave comes in one cylinder, you have a scattered longitudinal wave, but also a scattered shear wave. Yes. And what is surprising for me is that after 200 distribution, we find again, I have not plotted the scale, but we have again, not a coherent, but a shear wave, a mean shear wave that is present in the map.
No, inside you cannot have outside something on the left-hand side because it's forbidden by synthetization. What would be the limitation of that shear wave?
This is a 2D case, okay?
Yes, but in 2D, what would be the limitation? So,
in 2D,
normal incidence, any solid flow with back shear wave.
I do not agree. It can be the case for longitudinal wave in 3D with spheres. You have a symmetry when you have a sphere and a bulk longitudinal wave coming on a sphere. You have a symmetry and you excite only one shear wave, not the two shear waves. So we cannot talk about polarization. In 2D case, this is not a problem. We have polarization, we have wave conversion, and this wave conversion resists to the other.
It's not that you establish any elastic body, normal incidence doesn't matter how complex that will be. It's only the wave, it comes back normally as a sound, and there is no way you can direct shear because of symmetry. Normal incidence, back. If you have sort of non-normal incidence, yes, you can.
I don't really understand what you said. Because the cylinder, we have not normal incidence, we have a curvature of the cylinder, so we have wave conversion. There is no frontier.
No shear in the front.
Sorry?
Inside, you can have shear from one thing to another. But outside,
Why? If I take the expression, we have here expression of wave conversion. This term of the matrix reflects conversion transverse wave to longitudinal wave, and here longitudinal wave to shear wave. So I don't understand why you cannot have wave conversion in a system.
I think let's only go on this discussion later. It's okay.
Okay, I don't remember where I am. So, to finish with the question, so the good question, but I have not the answer. It's complicated. No, just to finish with that, sorry, I made the mistake on the wavelength. I think the wavelength is larger than the radius. But here, from this result, we can extract the effective properties of the coherent wave. We can obtain the effective wave number, so the phase velocity and also the attenuation. So, in the following of my talk, I will present you results and the influence of resonances and also on positional correlation between scatterers and elastic wave, and I will use this numerical code to obtain results. So let us see now the influence of the positional correlations between scatterers on elastic wave. So first of all, I want to start my talk, the talk of this part, about the hyperuniform distribution. That is the new strategy used in metamaterials to control wave, and it is based on a very simple assumption. If we are in the simple scattering regime and we consider point scatterers, we know that the intensity scattered by a random distribution of point scatterers is proportional to the structure factor. The structure factor is given here. This is can be seen as the representation of the distribution in the Fourier space. So the basic idea behind the hyperuniform materials is if we cancel the structure factor inside a region, a certain region in the Fourier space, we can have scattered intensity that become zero. So if I take a purely random distribution, there is no correlation with this distribution of scatterers. No correlation except the non-overlapping condition, obviously. We can see that the structure factor is totally random also. And what we want to do with hyperuniform materials is to cancel, in the case of my work, but this is the same for my colleague in Le Mans, it is to vanish, to cancel the structure factor in a disk here with a certain radius. So to do that, we have to check the distribution here with the constraint that we applied on the structure factor. I do that, I move all the particles in my box here, and I can see that we have a low values that happen in the structure factor. I continue to obtain a structure factor that is really zero around the origin in the disk that I as I know. So just the radius of the distribution is linked to two parameters. The first one is obviously the concentration of particles, and the second one is the parameter key that is the hyperuniform degree, or in literature we can see the stealthiness degree. This parameter is very important for hyperuniform distribution. If we have a distribution with a parameter key that approaches zero, the distribution approaches a Poisson distribution. But if key approaches P on 4, the distribution approaches that of a periodic distribution with a square mesh. So we can
little c.
Sorry.
C, the little c.
CA is a velocity. It is the velocity of the homogeneous matrix.
But this is an elastic material, so you have 2c.
No, I don't talk about elastic or acoustic. In the next slide, I will talk just one time to acoustic wave. But yeah, it can be speed of sound in liquid or bulk velocities. It's not complicated, but there are codes in internet that are really really fast, and yeah. There are two. We have during the PhD thesis of Adrien Roglic, we make our code, but it was not so fast. And in internet, in the net, we find the code of the Torquato team. Torquato is the boss of hyperuniform distribution. And in his team, there is a code very powerful. This is, in fact, an assumption of the simple scattering regime. If we are in a distribution that multiple scattering can be neglected, and we are in the simple scattering regime, we know that we have, at the first order, we have this relation. Yeah, but this relations, this is true in lots of cases. But the hyperuniform distributions come from are first studied by people who work with electromagnetic waves. So the assumption of point scatterers is more valid in their case. In acoustics, it is problematic, but you will see that it is not so problem. You have. I can reply to this question in the next slide. Sorry? Not understand.
Because we can see that clearly, this absolutely square. So you can write the term. One is n equal to n, another one is n equal to n.
Sorry, I don't understand.
What is square? And the diagonal term is always one.
No, sorry, I don't understand.
What you write a square?
Yeah.
As the sum multiplied by its complex quantity, right?
Yeah.
So you can write that as a product of two sums.
Yeah.
Right? And now the diagonal term, when n is equal to n, never vanish.
No, you talk about
Right.
this value, in fact. The value at the center.
I'm talking about the structure factor.
The structure factor.
Yeah.
You talk about the position at the zero. Isn't it? No?
No. The summation.
Yeah.
The summation from n.
Yeah.
You can write this as the sum multiplied by its complex quantity.
Yeah.
Right?
Yeah.
And so we have two sums multiplied together.
Yeah, the complex
one
quantity.
The index is n, and another one index with n.
Yeah.
And if n is equal to m.
Sorry.
If the n is equal to m.
Oh.
Then the diagonal term.
Yeah, I don't know.
Complex conjugate always multiply equal to 1. And if they are point particles, the non-diagonal terms will always cancel. In fact, this is what happens in the famous physical problem for the critical opacity.
Okay, yeah.
That's what happens.
Okay, I'm not sure.
Yeah, so you have two mixtures, the only transition temperature, they are transparent, and suddenly it becomes opaque. And so it depends on the particle size.
Okay, yeah.
Okay.
Okay. Well, we can talk together after. I'm not sure to have really understand that.
I think the point is you cannot have S0.
Yes. No. Because the complex conjugate, that's right. One has plus a of xn, the other one has minus I k.
Again, I think we perhaps ought to end on this point.
To finish with the characterization of the hyperuniform distribution, that I want to show you the pair correlation function that is used on the multiple scattering theories, and this pair correlation function can be seen as a measurement of the correlations in a distribution. You can see that if we increase the hyperuniform degree key, we can see that we have a strong peak that appears on the pair correlation functions, and this peak is followed by oscillations. These are the signatures of strong correlations in the distribution. I have not finished with this parameter. I haven't introduced the key parameter, that is the hyperuniformity degree, but we can also define a cutoff frequency for the transparency of the wave. So we know that we can, when we cancel the structure factor in a certain region, we can have transparency, but this transparency is not valid for all the frequencies. In fact, this transparency is possible, is allowed only if the frequency is smaller than the cutoff frequency here. So we can see that this cutoff frequency depends on the concentration and also on the key parameter. If we want a large domain of large frequency interval of transparency, we have to have large concentration and also large value of the key parameter. So, just for one time, I will show you result on coherent acoustical. Just this is experimental results that we have obtained at the laboratory with my postdoc, my Ludovic Alaix, my postdoc, make distributions of steel rods immersed in water. He manufactures three distributions with different values of the parameter P. The first one, P equal to 0, corresponds to a Poisson distribution, so a random distribution with non-overlapping condition. And we have two hyperuniform distribution. We have here the structure factor for the random distribution, and the structure factor is random also. We find again that the structure factor for the hyperuniform distribution vanishes in a disk here, and for the structure factor for the hyperuniform distribution with a large value of T, in fact, we have a structure factor that is very different to the previous one. In fact, we have values here that are very strong. In fact, we cannot. We have the signature here of the periodic distribution. If you have a periodic distribution, you will have line here that corresponds to the periodicity.
So the lattice orientation is aligned with the periodic lattice, but it's not clear where your orientation is.
The question is the orientation comes from the fact that it is a random distribution. So if you make another random distribution, you have another orientation.
What is the typical value of capital N?
The value of?
The number of particles.
Sorry, I forget. Few thousand. It's complicated to. In fact, I have not the exact number, but we have a few hundred steel rods. In fact, it is complicated to have. We need lots of particles to have a large concentration, but it is complicated to have parallel steel rod. So for experiments, not our samples have maybe 10 in a radius. We have maybe 10 cylinders in the direction of propagation.
The last figure of this mean that there's a transition from hyperuniform to colloid.
Beginning, sorry.
This last figure here.
Yeah.
Does this mean that there's a transition between hyperuniform and this kind?
This case, yeah,
Yes.
yeah. We are very close to periodic distribution, and we will see here on the radar.
It's monotonously high. When you increase high, it becomes more and more colloid.
I'm not sure. I think yes, but I'm not sure. So no, just before, I want to tell you to explain you the experiment that we do. We put here at the center of each distribution an hydrophone, and this hydrophone will generate point source and we study the propagation of the point source here in the distribution. And with another hydrophone, we go around the distribution and we measure the acoustic pressure all around the distribution. So you can see here the acoustic pressure measured for the random distribution, for the first hyperuniform distribution, and for the second one. I put also maps, the figures, the acoustic pressure is plotted as a function of the frequency here, and also the angle theta that corresponds to the round around the distribution. We have here the cutoff frequency, it's black the shed line here and here, and we can see that the acoustic pressure for the hyperuniform distribution is very close to 1 in all the angle here for frequencies smaller than the cutoff frequency. We find also this result for the second hyperuniform distribution. But if we look for the random case, this is not the case. We have regions where the acoustic pressure is close to 1, but there is also direction where there is a small pressure. So it is an effect. This is a signature of the transparency of hyperuniform distribution to acoustic waves. Now I want to plot the directivity of the source of the wave that propagates in the distribution. So we can see I have plotted some the acoustic pressure with radial plotting here for this frequency smaller than the cutoff frequency, and for the frequency in orange that is larger than the cutoff frequency. We can see that for frequencies smaller than the cutoff frequency, we have an omnidirectional acoustic pressure, and this is the case for both hyperuniform distribution, but not for the random distribution. And if we look the directivity at frequency larger than the cutoff frequency, we can see that for the hyperuniform distribution, as expected for the first one, we have not an omnidirectional directivity, but for the second hyperuniform distribution, we have scattering in privileged directions. So this is a signature of anisotropic scattering, and this corresponds to here to the values you can see here of the pressure. And if I look the scattering factor, it corresponds to values that we can see here. So hyperuniform distribution are very interesting because we can see acoustic transparency, but we can see also isotropic scattering and also anisotropic scattering in privileged directions. So this kind of distribution, this kind of correlations are very interesting in the context of the control of acoustic waves. It is very robust. It is very robust because it is a random media, it is a random distribution and not a periodic distribution. We have performed numerical calculation by perturbing the position of distribution, and the acoustic transparency resists to this perturbation. This is not the case for a periodic media. In fact, this is the potential of hyperuniform distribution. They are random distribution. Okay? So, hyperuniform distribution are very interesting, but in fact, they are a little bit complicated it's complicated to fabricate samples, and especially three-dimensional samples. So I want to talk to you about another kind of correlation, very simple kind of correlation that we can see at every time in every structure. This is a short-range correlation. The basic idea is, if I take a box and I put some few scatterers in the box, I can see here the pair correlation function that is 0 for radii smaller than the diameter of the particle, and this pair correlation function is close to 1 for larger value of R. Now, if I put other particles in the box, we can see that with 10%, we have a small peak that happens, and we add again and again particles to finally obtain very highly concentrated material, but we can see that we have strong correlations on the pair correlation function. In fact, we have a signature which is very similar. We have a pair correlation that is very similar to the hyperuniform distribution. It's a large peak at the beginning of the function and after oscillation. In fact, these correlations can be introduced in distribution very simply by using an exclusion distance between the centers of a pair of particles. So if I introduce the exclusion distance be superior to a diameter, for 2 diameter, 2.5 diameter, 3 diameter, you can see here it corresponds to the exclusion distance to the circles with color. We can see here on the pair correlation function that we obtain for the same, this distribution has the same concentration, obviously. We obtain a very strong effect on the pair correlation function with the peak and the oscillation. So the question is now, can we obtain also transparency and isotropy of the scattering with this very simple kind of correlation? So now I come back to elastic wave. Yeah.
Well, it's about the same, or there are different models, right, for pair correlations?
No, it's numerical. I calculate the pair correlation function, but it is a mean. It is the average pair correlation function. It is numerically.
Do you think this would match with Valier-Brasier or not?
So?
Valier-Brasier is a model of pair correlation, which takes into account the density of particles. I was just wondering if this will match with.
Yes. I don't use percussivic, but it's the same. Yeah. You can
use that when you get close to one of the things closer or increase the volume fraction. You always get to
in fact, it is very simple. To understand why there are oscillations. In fact, if I take one particle, okay, this one, there are in a first ring with other particles, and again another ring, and this cause this is the response of this oscillation. Okay, so let's come back on coherent elastic wave. I come back with solid materials with longitudinal and shear wave. The transparency of wave corresponds to the fact that if we have a coherent wave that propagates in a heterogeneous medium, the distribution is transparent to the wave if the coherent wave does not attenuate. Okay, so if the attenuation of the imaginary part of the coherent of the effective wave number is 0. So I use the code Musca to calculate the attenuation of the coherent longitudinal wave on the left and the shear coherent wave on the right in a hyperuniform distribution of cavities filled with water in an aluminium alloy. You can see here that we have an attenuation. There are here and here the cutoff frequency. We can see here that we have a region, an interval of frequency, where the attenuation is 0. So you can say that the medium is transparent for longitudinal wave, but this region is very small. For shear wave, we have a larger interval, and it is very strange, but we have a cut that appears on the attenuation. So we obtain also the transparency for longitudinal and also for shear wave. Now you can see for the short range correlated distribution that we obtain very similar result for the longitudinal wave. The curve follow exactly the curve for the hyperuniform distribution, and it is quite the same for the shear wave. We have an attenuation that is not zero, but it is very small.
In the earlier case, when you had last case, the boundary condition was directly on the displacement. Directly boundary condition of displacement, yes?
No, I don't talk about that, but I take into account the elasticity of the rod. It is a steel rod.
Unity of fraction and displacement.
I have, sorry?
So it's not directly bonding.
No.
And here also you have water filling the holes.
I don't understand. In this case,
your cavity here.
in the cavities, cavities are filled with water. No. And we take into account the presence of the acoustic wave in the water. That is your question?
Yes, but what's the boundary condition that we use?
Oh, but the continuity of stresses and normal displacement.
Yeah, fraction and displacement.
But here I am in a frequency regime where there is no resonances. But in larger frequencies, there are lots of resonances in this case. Resonance due to whispering gallery modes propagating inside the cavities. So just to finish with this slide, I present you the models that we derived with Jean-Marc Renoir and Francine Huppé about the propagation of elastic wave in three-dimensional solid materials. With Jean-Marc Renoir, we have also worked on the model of Connoir-Morris that is adapted to the case that is derived for the case of cylinders. And we have added in this model the pair correlation function. You can see that the pair correlation function can, it's not perfect, but the pair correlation function can show that we have very small attenuation for the effective wave. I don't know why the result for the shear correlated media is very good. We have a very good agreement between the Connoir-Morris model with the pair correlation function and the Musca code. For the hyperuniform distribution, I don't know why we have less good. So I finish with the positional correlations. We have obtained very similar results for short range correlation. We have obtained very similar results for the short range correlations than hyperuniform distribution. I don't show you result on isotropy, but we obtain the same results on the isotropy and the anisotropic distribution. Experiments are really more complicated in the case of elastic wave for hyperuniform distributions because samples are complicated to create, to elaborate. So now I want to talk to you about another topic of another influence on a coherent wave, that is the influence of steep wavelength resonances on coherent elastic wave. This is work that I performed with my colleague Régis Founan-Burger at the Jean-Laurent Ballambert Institute. The problem is there are lots of results on the effect of steep wavelength resonance on coherent acoustic wave, but on elastic wave, there is nothing. We want to use steep wavelength resonances, but the problem is which kind of resonances can we use to modify the properties of the coherent wave, the coherent elastic wave. If we look at the sub-wavelength resonances, there are two resonances, the monopolar resonance and the dipolar resonances. The monopolar resonance of the sphere is due to the compressibility contrast between the particle and the matrix. But in the case of solid matrix, the only resonance that we can use, it is a resonance of a bubble in a soft materials, or air cavity in a soft material. And moreover, this resonance affects only the longitudinal wave. So it is not very interesting because there is no wave conversion. It is like the acoustic case in fluid media. So our strategy is to use dipolar resonances that are based on the density contrast between the particle and the matrix. And the problem is the resonances exist. There are two resonances. These resonances exist only for heavy particles, but it is not really a big problem. And the good, what is very interesting, is that the resonances affect both longitudinal and the shear wave. And it is very interesting because there is no strategy in the literature and in the community on the control of shear wave. So we want to do that, and for that purpose, we start by the first work to do was to study first the interaction of a unique particle with an incident plane wave. So we study a rigid moving sphere. It is a rigid particle, a rigid sphere, but it has a finite mass and it can move in the matrix. So if we have an incident longitudinal wave that is coming on the spherical particle, the displacement field associated to the incident longitudinal wave that propagates in the z direction, this incident wave is also polarized. It is a longitudinal wave. It is also polarized in the z direction. So we can see here that the particle moves with the translation displacement that is polarized in the same direction than the polarization of the incident wave. If we look for the shear wave, we can see that the shear wave here propagates and it propagates in the z direction again, but it is polarized in the x direction. And the interaction of the particle and the incident plane wave leads to two displacements of the particle, a linear displacement, a translational displacement. As the longitudinal case here, the translational displacement is parallel to the polarization of the incident plane wave. And we have also a rotational motion here for the particle. So if we have a longitudinal wave, we excite only translational displacement. If we study a shear incident wave, we have two motions, a translational and a rotational one. So, using the second Newton's law and applying the boundary conditions that are the continuity of displacement at the surface of the particle, we calculate the scattering coefficient of a rigid moving sphere embedded in a solid matrix. Using a low frequency approximation, we can obtain from the scattering coefficients the characteristic equations, one for the translational motion and one for the rotational one. If we neglect the viscoelastic dissipation in the matrix, we can obtain an exact expression of the resonance frequency of the dipolar translation resonance, and this resonance frequency is proportional to Ct, that is the shear wave velocity in the elastic matrix. We can also see that we have the density contrast, rho theta, that is the contrast between the density of the particle to that of the matrix. It is very interesting because this formula is very similar to the famous formula obtained by Minert for the resonance of a gas bubble in water. Sorry? The ratio.
Which way up? It's rho tilt. You made some assumption that density contrast has to be large.
In fact, I have no assumption on the density of the particle, but with this formula we can see that we have no resonances for if the density contrast is low. But there is no assumption. in this case. The only assumption in the long wavelength regime for longitudinal wave. It is exact for shear wave.
So we need to assume that it means soft, like it's soft. We assume that.
Not necessary. If you have a soft material, the resonance frequency translates in the low frequency. Okay? But in the case I will show you, we use epoxy resin. Epoxy resin, the shear modulus is close to 1 gigapascal. It's not so soft, and we have a strong resonance. There is no assumption on the density to contrast and on the shear modulus of the matrix. Okay. Before to study the propagation of coherent elastic wave in solid, I want to show you the scattering cross sections in order to well understand the scattering by a unique particle. You can see here, if I calculate the scattering cross section for the longitudinal, or this is for a longitudinal incident wave for the beginning, with a longitudinal scattered wave in blue and transverse wave in orange, we can see that the scattering cross section is very weak for the longitudinal case, but the scattering cross section for the transverse scattered wave is very strong, very large, and we can see that we have a strong effect of the dipolar translation resonance. So we expect that when we study the propagation of coherent longitudinal wave, we will have lots of a strong wave conversion due to the interaction of the longitudinal wave and the particles. We have a large wave conversion, not only at the resonance. Now the scattering cross section for the shear incident wave. We have no wave in blue. This is again the scattering cross section for the longitudinal wave. This is the same color, but we can see here that the wave conversion in this case is very weak. Okay, but now if we look the scattering cross section for the transverse scattered wave, we can see two peaks that appear, and these two peaks correspond to the two dipolar resonance, the resonance in translation here and the resonance in rotation here. So we expect in this case not conversion, not very small, very weak wave conversion, but we expect that we have strong scattering at the resonance. So you can see here results that we have obtained experimentally and theoretically on coherent longitudinal wave for a small concentration, just 2% of tungsten carbide spheres embedded in an epoxy resin. We have a dispersion, a small dispersion around the translation frequency resonance, and also a peak in the attenuation for the coherent wave. And I plot also the models that we derived with Jean-Marc Renoir and François of multiple scattering based on the multiple scattering theory. I plot also the same model, but by neglecting the wave conversion. In the case of 2%, it is not really interesting because the effect is weak. Now, if we look for 5%, we can see that we have a stronger effect on the dispersion, the velocity, a strong peak on the attenuation, and we can see also with the D-shaped curve that the model, the MST model that we derived, is in good agreement with experiment, both for phase, velocity, and the attenuation. Nevertheless, the model, if we neglect the wave conversion, is a poor agreement, so it is the signature that the wave conversion has to be taken into account in the model. So now for 10%, sorry, we obtain a similar result with a strong dispersion on the phase velocity and a strong peak of attenuation. Something that is very interesting is we measured a frequency shift of the attenuation peak here as function of the concentration, and the model predicts this frequency shift. So we have obtained an interesting result on these materials. Now we try to use short-range correlations to optimize the effect of this resonance. So we make sample with a small concentration of beads. It is 2% of concentration, and we have changed the exclusion distance between the particles. We increase the exclusion distance, and we can see that the dispersion of the phase velocity increases with the value of the exclusion distance b, and the peak of attenuation also increases with this exclusion distance. So it is very interesting because short-range correlation can allow us to optimize the effect of a strong subwavelength resonances. Another fact, another interesting fact is that if we take if we use the MST model that we derived and we replaced the value of B that is given by the Hall correction by the value B that we put in our sample, we can obtain a very similar result. The MST model captures the effect of the optimization, the effect of the increasing of the influence of the resonance on the coherent wave. So we can use this we can use the short-range correlations, and we are able also to model these properties. Okay. Now, just result on coherent shear wave. It was really difficult to obtain this measurement, but we have done that with a new an original technique. I show you result for 2% of beats, 5%. This is the same samples. We obtain a very good agreement with MST model, but I want to go next. I go next with the very interesting case of coherent shear wave. With the sample of concentration 10%, we obtain a result very strange. In fact, we have a strong discontinuity on the phase velocity, and it was complicated to understand what is the reason of this discontinuity. The MST model gave us a solution that is in bad agreement with the experimental result. So we come back to the MST model, and instead of use the approximate expression of the effective wave number, we choose to solve numerically the characteristic equation given by the MST model, and we obtain two modes for the characteristic equations. One first mode in orange and another one in green. If I look at the attenuation curve of the coherent wave, I can see that the measured attenuation follows the dispersion curve of the first mode, and after that follows the attenuation curve of the second mode. And if we look at the phase velocity, in fact, it explains why we have this discontinuity. The phase velocity follows the dispersion curve of the first mode, and then after the resonance, the rotation resonance, that follows the dispersion curve of the second mode. So we have shown experimentally and theoretically the existence of two propagation modes, and this result have been obtained 30 years ago in 90s on colloids, and it was for very highly concentrated colloids. In our case, we have just 10% of particles, but currently we are not able to explain the physical rhythm, the physical meaning of this appearance.
So these fields are bounded, I suppose.
Sorry?
Is green curve
Yeah.
mounted from above or put in place?
I don't understand. You want to say?
Does it go to infinity?
Yeah, not infinity, but the attenuation in the low frequency is very, very large.
But see, on the left side, see.
No, in fact, there is a discontinuity. I don't remember, but I think there is a cut, and it is in a low frequency. It goes in backward direction. So you have a negative phase velocity, but it's complicated. I have just finished with the conclusion. So just to say you that we have developed different statistical modelings of elastic wave propagation in multiple scattering media for elastic wave. We have also developed, this is very important, the MISCA code with the 2D version for cylinders that is validated for fluid and solid matrices. The 3-dimensional code for spheres is validated for fluid materials, fluid matrices, and it is in progress for the solid matrices. We have also obtained a new experimental result on coherent elastic wave, both for longitudinal and shear wave. We have also obtained new result on hyperuniform distribution and the transparency and isotropy of the scattering. And now we have lots of future work that we can talk if you want.
Thank you very much, Amy. If anyone has the stamina, feel free to ask all the questions. Otherwise, it's time for the traditional photo. Who's the seminar photo? Right, thank you. So we will gather at the front and take photos. Record our seminars.
Okay.
Do you want to put back onto your, choose something that you want to show in that photo. Or you can show your titles.
Hyperuniform distribution?
Yeah, that's a nice
That's good?
Yeah, that's a nice one. On the photo.
So we can just
Thank you very much. Can we say thank you again?